Greetings to all. In this video, we will be simulating a series resonant circuit using MATLAB Simscape. So what is Simscape? First we will be peeking into it. So here is a library browser for the MATLAB Simulink. As we click on this library browser, we get so many libraries like Simulink, Aerospace, Blockset, Audio, and here at the bottom we find a Simscape. So in Simscape, we can find electrical, fluid, multi-body, or any kind of. You can do a mechanical simulation also, but we will be sticking ourselves to electrical. So in electrical, I use the simple components or the P-spice components, which are known as specialized power system. So these are the fundamental blocks, and here I have used the sources, and in machine and in power electronics, I have used these kinds of devices. So this is a Simscape and I have taken every component from this place only. So another way of extracting components from the library browser is by double clicking and writing about that block. Like we want voltage sensor. So here comes a voltage sensor and this is a voltage sensor which I have been using here. So now coming back to the series RLC circuit. So in series RLC circuit, this is a circuit which basically consists of a AC source and a resistance, inductance and a capacitor, which is shown by the color green. So here is a voltage source and we'll be going into the voltage source, double clicking it. So I have taken a 10 square root 2 is the peak value, or the 10 is the RMS value of this AC current or AC voltage. 40 Hertz is the frequency. Similarly, I have taken resistance. The value of resistance is 1 and tolerance is 5%. You can change tolerance according to your circuits. In inductance, I have taken 1 millihenry inductance, and for capacitance, I have taken 0.01 or 10 millifarad capacitor with a series resistance of very low, or you can keep the series resistance to 0 also. Similarly, for inductance, you can put parallel conductance, to 0 or whatever you want to. So these are the RLC circuit. Now comes the measurement circuit. So these are the ammeter, voltmeter. Why 3 voltmeter or 4 voltmeter I have kept? Because this voltmeter will be measuring the voltage across resistance. Second one will be measuring across inductance, and third one will be measuring across the capacitor. And these are the go-to tag which are used for the convenience, because I have tagged here VR, that the voltage is VR here, and this voltage is again I am measuring at this point. Similarly, VN I am measuring here, and VC I am measuring here, and V0 is the total output voltage. Now one interesting fact in Simscape is the solver configuration. You have to ground the circuit and you have to keep the solver always. So this is known as reference. So in circuit we always put the circuit with the reference circuit, and this is a solver, and this solver configuration is simple. It wants you to write some the step size or the sample size. So I am using backward Euler method, and this is the most common method which is used, and the sample time is 0.1 millisecond, and the rest you can keep unchanged. The rest thing you keep unchanged. The one very small trick in this is the use of this converter. This converter converts Simscape into the Simulink, because the scope is from the library of Simulink. If you go back to the library, we are putting every component from this library, Simscape, and the scope we are finding is from this library. So this is a floating scope or other scope. This scope I am using. So to connect this circuit with the Simulink circuit component, we use some connectors. So these are connectors. These are called Simulink connectors. Okay. So this is everywhere wherever the signal is going from the Simscape circuit to the scope. This is the scope. So now I will be running the program. I am putting it for the 0.1 second. So now I will be putting. So what will happen is, basically what happens in the series resonant circuit, that there are three values: the resistance, the inductance or the XL, or we call it the inductive reactance, and the capacitive reactance. So at a particular frequency, In this case, the frequency you can calculate like this: 1 upon square root of LC. L is the inductance and the C is the capacitance. So it is coming around 50 hertz. I have deliberately taken it 50 hertz. So the frequency for our case is 50 hertz, and currently I have taken 40 hertz. So at this point, XL will not be equal to XC. So the circuit will not enter into the resonance. So let's run the circuit. So this is compiling and this is running the circuit. So now I am going to see the scope. So here you can see, if you remember your series resonance circuit, you will see that in resonance the circuit behaves as if it is totally resistive load, or the circuit is resistive. But here you can see that V out, the voltage in blue in the first figure, this figure, is lagging the current I out. That means the circuit is capacitive. You can see here the circuit is capacitive. Here you can see that blue one is coming after the red one. Okay, so this shows that the voltage is lagging and current is leading. So this circuit is capacitive. Currently the capacitive. Why it is capacitive? Here I have shown all the three voltages. This is the red one is the voltage across resistance, and you can see that yellow and blue are the voltage across capacitor, this yellow one, and blue one is the voltage across inductor. So these both are of opposing nature, but because the yellow or the capacitive voltage is higher, it is not cancelling out the inductive voltage. So at resonance, what happens? This both things cancel out each other, and the circuit behaves as a pure capacitive circuit. So at this point, the voltage across this VL should be equal to VC, and it should be cancelling out each other. So here you can see, so we'll be ignoring the transient. So here you can see that the V out is in phase with the I out. That means the circuit is capacitive. And here also you can see that the inductive voltage is cancelling out the capacitive voltage with the same magnitude. So this is cutting with the same magnitude. So the ultimately what we are getting is a resistive circuit. So it is not that inductor and capacitor are not working. They are working, but their voltages across it are cancelling out each other. Like we can see here in the second figure, the yellow one is equal and opposite to the blue one. The yellow one is the voltage across capacitor, and blue one is the voltage across the inductor. So these both are cancelling out each other. What happens if I increase the frequency further to 60 degree? Now again the circuit will not be operating in a resonance. It will be working in an inductive manner, as if the effective circuit is inductive. So now the current will be lagging. Now what is happening? The I out, the red one, is lagging the blue one, or V out. Here you can see. So at this moment we can see that the blue one is lagging the red one. Okay, or blue one is leading the red one. So blue one is the voltage, so voltage is leading, and here you can see this blue, which is the voltage across inductor, is higher than the voltage across capacitor. So it is almost touching over 5 voltage, and this one is less than 5. The blue one, the yellow one, is less than 5 volt. The peak of the VC, or the voltage across capacitor, is not touching 5, whereas this blue one is crossing 5 voltage. The peak voltage of voltage across inductor is more than 5 volt. So here we can say that as the frequency increases, the circuit becomes more and more inductive, and as the frequency is low, the circuit becomes capacitive. And at a particular point, which we can calculate from here, resonating frequency 1 upon square root LC, we can find that at 50 hertz is the sweet spot where the resonance is happening. So this is resonance, where we can see that it is in phase with the voltage is in phase with the current, and here the VC, the capacitor voltage, and the inductor voltage are cancelling out each other. So this is all about for the resonance circuit. In next video we will be learning about the parallel resonance circuit. So this file you can take from the description also. Thank you.